Right now, we are traveling around the center of the Milky Way. We do not feel it, we do not see it, but we move at about 220 kilometers per second, dragged by the orbit of the Sun around the galactic nucleus. It is a constant, silent displacement that takes approximately 230 million years to complete one revolution. That center is not a bright star, nor is it a cluster visible to the naked eye. It is hidden behind a wall of interstellar dust that blocks optical light. For centuries, when astronomers looked toward the constellation of Sagittarius, they found stellar density, but not the real heart of the galaxy. Visible light simply does not pass through that region clearly. Dust absorbs and scatters radiation, especially at short wavelengths. What seemed like a void was not absence, but concealment. The galactic center is about 26,000 light-years away from us. That means any image we obtain today shows the state of that place when on Earth the first forms of cave art were beginning to emerge. There is no now when we speak of that distance. We only see the past. For much of the 20th century, the nucleus of the galaxy was a speculative region. It was inferred that there must be a massive concentration at the center because the stars of the galactic disk orbited something. But that something had no defined shape. It was not distinguishable in the visible spectrum. It did not emit an obvious signal that would allow it to be identified as a conventional star. The change came when astronomy stopped depending exclusively on visible light. Radio astronomy opened a new window. Radio waves passed through dust much more effectively than optical light. Suddenly, regions that seemed opaque began to reveal complex structures. The center of the Milky Way stopped being an imprecise blur and began to show activity. In the 1950s and 1960s, intense radio sources were detected in the direction of the galactic nucleus. One of them turned out to be especially compact and energetic. It received the name Sagittarius A. Later, an extremely small and variable component within that region was named Sagittarius A*. The asterisk indicated something peculiar. It was not an extended source. It was point-like, concentrated, difficult to explain with conventional stellar models. However, detecting a radio source is not the same as understanding its nature. It could be hot gas. It could be a superposition of objects. The fundamental question remained open. What type of object can concentrate so much energy in such a reduced volume at the center of a galaxy? But measuring those stars was not simple. The nucleus of the galaxy is a crowded region. The apparent distances between stars are minimal from our perspective. In addition, the Earth's atmospheric turbulence distorts images, even in infrared. It was necessary to combine large aperture telescopes with advanced optical correction techniques. For years, teams at different observatories systematically pointed toward the same spot in the sky. They were not looking for a spectacular flash. They were looking for tiny displacements, almost imperceptible changes in the position of individual stars. The objective was to reconstruct complete orbits. This approach required patience. A stellar orbit around the galactic center can take years to close. One observing season was not enough. Decades were needed. Meanwhile, the conceptual image of the galactic nucleus began to change. It was no longer just a dense region. Radio and infrared data showed clouds of ionized gas, intense magnetic fields, and a notable stellar concentration. It was a dynamic environment, complex, energetic. However, at the exact center of that scenario, there seemed to be something that did not shine like an ordinary star, something compact, something that acted as a gravitational reference. The idea of a supermassive black hole began to consolidate as a plausible hypothesis. It was not a sensationalist proposal. It was a logical consequence of the data accumulated in other galaxies. Many active galactic nuclei showed signs of harboring extremely massive and compact objects. If that happened in distant galaxies, why not in ours? The difference is that in other galaxies, relativistic jets and intense emissions were observed. The center of the Milky Way, in contrast, seemed relatively calm. It did not show the luminous violence of a quasar. If there was a black hole there, it was in a low-activity state. But calm does not imply absence of gravity. Mass, even when silent, leaves marks on motion. At the end of the 20th century, the strategy became clear. Follow the stars closest to the nucleus and measure their trajectories with increasing precision. If those stars described closed orbits around an invisible point, and if the velocities reached extreme values, there would not be many possible physical alternatives. The galactic center was no longer just an opaque region. It was a gravitational laboratory, a natural experiment that had been running for billions of years. What was at stake was not only the understanding of the nucleus of the Milky Way, it was also a direct test of the existence of a supermassive black hole in our own galaxy. The stars began to reveal a pattern. They did not rotate randomly. They did not disperse. They orbited a precise dark and compact point. To turn a suspicion into certainty, someone had to sit in front of the same point in the sky for years. It is not a romantic image. It is a repetitive task. Point, measure, correct, measure again, over and over. At the end of the 20th century, two groups focused on the nucleus of the galaxy. One worked at the Keck Observatory in Hawaii, the other with telescopes of the European Southern Observatory in Chile. They had a common mission: to follow the movement of the stars that live near the galactic center. The technical problem was enormous. Those stars are 26,000 light-years away. From here, their apparent separations are minuscule. In addition, the Earth's atmosphere distorts the images, makes the stars twinkle and blur. To see their real positions, astronomers had to resort to adaptive optics, systems that deform a mirror in real time to compensate for air turbulence. With that technology, individual stars began to be resolved in the immediate environment of Sagittarius A star. They were not calm stars. They moved rapidly. They changed position from one year to the next in an evident way. Some described closed trajectories around a point that did not shine. Among all of them, one would become the protagonist. Today, we know it by the name S2. It is a massive star, type B, much hotter and more luminous than the Sun. But what made it special was not its brightness, but its orbit. S2 completes a turn around the galactic center in about 16 years. That period is surprisingly short for an orbit at that scale. It means that the star gets very close to the central object. At the closest point, the periapsis, it passes at a distance of a few tens of astronomical units, that is, a few times the distance between the Sun and Pluto. On a galactic scale, that is equivalent to skimming the abyss. When S2 approaches that point, its speed skyrockets. It reaches values of thousands of kilometers per second. It is a star that, for a brief stretch of its path, moves at several percent of the speed of light. None of that fits with a normal center composed of stars distributed in a wide volume. This is where the physics of Newton and Einstein comes into play. If the shape of an orbit and the period of the star are known, the total mass enclosed within that orbit can be calculated. It is the same principle we use to estimate the mass of the Sun by observing the motion of the Earth. The difference is the scale. In the case of S2, the calculations indicate that within its trajectory there is a mass equivalent to about 4 million suns, concentrated in a very small space. That concentration of mass has consequences. If the center were occupied by a dense cluster of stars, that cluster would be unstable. The stars would collide, merge, disperse. A collection of compact objects, such as neutron stars or small black holes, would also be problematic. Such a swarm would collapse or produce detectable radiation emission. None of that is observed. The data push toward an uncomfortable but simple conclusion. That mass must be concentrated in a single, extremely compact object. In other words, a supermassive black hole. The strength of this conclusion is not in a spectacular image, but in the coherence of the orbits. Year after year, the measured points of S2 were added on the plane. At first, they looked like isolated positions. Then they began to form an arc. Over time, the arc closed and became a complete ellipse. The entire trajectory surrounded the same dark point. That point did not move with respect to the galactic background. It was not a wandering star in the nucleus. It was a stable center of mass, the place around which everything revolved. With the advancement of instrumentation, astronomers did not stop at the classical orbit. They looked for subtler traces, relativistic effects. In an extreme gravitational field, the orbit of a star is not a perfect ellipse. The point of closest approach shifts slowly with each revolution. This is the precession of the periapsis, a phenomenon predicted by the theory of general relativity and previously confirmed in Mercury's orbit around the Sun. In the case of S2, that precession was also measured. The orbit did not repeat exactly. Each cycle presented a small additional rotation. The magnitude of that rotation matched what is expected if there is a black hole of about 4 million solar masses at the center. It was not just a matter of weight. It was a direct confirmation of the extreme curvature of space-time in that region. Around S2, other stars were identified with orbits even closer to the central object. Some appear to complete their revolutions in even shorter times. Each new measured period reinforces the same story. In the nucleus of the Milky Way, there is an enormous mass concentrated in a small volume, whose best physical description is that of a supermassive black hole. It is important to note the type of evidence obtained. This is not a simple visual correspondence. It is not a "looks like a black hole." It is a dynamic verification. Measurements are taken, physical laws are applied, reality is compared with models. The option of a massive compact object, described by Einstein's equations, explains the data consistently and precisely. Alternatives become increasingly artificial. As the orbits were being completed, the galactic center began to cease being an abstraction even for the general public. The idea that the entire galaxy, including Earth, orbits a black hole entered popular culture. But behind that simple phrase lies decades of work, thousands of hours of observation and patience rarely shown in popular summaries. The image of S2 tracing its ellipse in 16 years around a point without light is in itself a powerful metaphor. A black hole does not shine. It has no surface. There is no incandescent ground. What emits light is the material surrounding it: gas, dust, remnants of stars. All of it falls toward the center, loses energy, heats up, and begins to radiate. To understand the object, you have to observe how what is about to disappear is illuminated. In the case of the center of our galaxy, there is a lot of material available. Massive stars throw off stellar winds, clouds of gas cross the central region. The gravitational field of the black hole captures a small fraction of that flow. That gas does not fall in a straight line. It arrives with angular momentum. It forms a clumsy, irregular structure, something we can call an accretion disk, although it is not a thin, orderly disk as in textbook diagrams. The surprising thing is that for the mass it has, the black hole at the center of the Milky Way is very dim. It could shine millions of times more if it devoured matter at the maximum rate allowed by physics, the so-called Eddington limit. Instead, it operates in savings mode. The accretion rate is extremely low. Much of the trapped gas does not become light, but rather useless heat and turbulent motion within a radiatively inefficient flow. At different wavelengths, astronomers have observed flares, small bursts of light that last minutes or hours, in infrared, in X-rays, in sub-millimeter. The luminosity increases several times or even hundreds of times above the usual level and then decays. It is as if, occasionally, a portion of gas reorganizes, compresses, heats up suddenly, and emits all its energy in a brief flash. The time scale of these flares is a clue. When something changes within tens of minutes near a black hole of 4 million solar masses, the region responsible cannot be very large. Characteristic times depend on size. If the brightness rises and falls so quickly, the origin must be just a few tens of gravitational radii from the event horizon, in the zone where space-time curves extremely. With instruments like gravity, an interferometer that combines the light from the 4 VLT telescopes, it has been possible to go beyond simple brightness variation. During some of these flashes, the apparent movement of the emitting point has been measured. What is seen is a hot spot, a knot of plasma orbiting very close to the black hole, at speeds of around 30% of the speed of light. The position of the point shifts, tracing a kind of closed arc while the brightness rises and falls. This behavior fits well with the idea of a piece of gas trapped at the inner edge of the accretion disk. A small region where the magnetic field intensifies, accelerates charged particles, and produces synchrotron emission in infrared and X-rays. These are processes we do not see directly, but which are reflected in the light curve and in the apparent trajectory of the bright focus. At the same time, observatories like NuSTAR have followed some of these events in high-energy X-rays. The results show that the spectrum of the flares extends up to tens of kilo-electron volts without a clear cutoff. It is a sign of extreme processes, with electrons accelerated to very high energies in an intense magnetic field. But even there, in full microscopic violence, the total energy released in a flare is small compared to what the black hole could emit if it were continuously devouring matter. In recent years, the James Webb Space Telescope has added another level of detail. Observing in infrared with unprecedented sensitivity and over continuous periods of many hours, it has shown an even more restless picture. The immediate environment of the black hole appears as a region of constantly flickering brightness, punctuated by more intense flares. It is not static fire, it is a surface that boils. Gas from stellar winds flows in, swirls, heats up, and sometimes lights up dramatically before falling or being expelled back into space. All of this occurs in a small volume of space compared to the solar system. The characteristic size of the bright ring, the region where the gas emits most intensely before disappearing, is just a few tens of millions of kilometers. Rarely has the contrast between physical scale and gravitational effect been so brutal. An object with a horizon smaller than Mercury's orbit, yet whose influence organizes the motion of hundreds of billions of stars. To see the edge of a black hole, a large telescope is not enough. Something disproportionate is needed. An instrument the size of the Earth. That was the idea behind an international network of radio telescopes that would work as if they were a single telescope. A collaboration distributed across mountains, deserts, and extinct volcanoes, united by a simple question. Can we map the shadow of the center of our galaxy? The technique is called very long baseline interferometry. It consists of synchronizing multiple radio telescopes separated by thousands of kilometers. Each records, on hard drives, the radio signal coming from the same point in the sky, with atomic clocks marking time with extreme precision. Then, all that data is brought to processing centers and combined. The result is as if the entire Earth were a single mirror at millimeter wavelengths. Before looking toward our galaxy, the network had already tested its power on another target, the supermassive black hole of the galaxy M87. It is much more massive than that of the Milky Way, billions of solar masses. It is also larger. This means that changes in its environment are slower. Gas takes days to complete an orbit near the horizon. For an experiment that needs to integrate signals over several continuous hours, that relative calm is a decisive advantage. In our galaxy, the situation is different. The central object is much less massive, about 4 million suns. That also makes it smaller. The gas orbiting nearby moves on timescales of minutes. What happens at the edge changes while the network of telescopes is building the image. For a system that requires the source not to change too much during observation, Sagittarius A star is a difficult target. Still, in April 2017, the network aimed at the heart of the Milky Way. 8 radio telescopes at 6 different locations observed the same region at millimeter wavelengths. Over several consecutive nights, they collected petabytes of data. At each antenna, the signal was recorded on physical disks, which were then flown to correlation centers. There was no way to transmit all that volume over the internet. The analysis was not a matter of weeks. It took years. The challenge was not only technical, it was also physical. The source varied. Brightness rose and fell. The structure of the gas changed while the Earth rotated and the network filled gaps in its virtual mirror. To obtain a stable image, new reconstruction techniques had to be developed. Instead of treating the observation like a long exposure photograph, models were built that accounted for the variability. Thousands of possible images were generated from the data and filtered according to their compatibility with the expected physics. On May 12, 2022, the result was shown to the public. What appeared on screen was not a sharp disk nor a perfect circular hole. It was a blurry, irregular ring with a darker central region, a compact structure of tiny angular size, about 50 microarcseconds, approximately the angle a donut would subtend on the moon's surface as seen from Earth, or the size of an atom held at arm's length. Behind that image are more concrete numbers. At the estimated distance of the galactic center, that ring corresponds to a physical diameter of about 51 million kilometers, something like 37 times the diameter of the Sun, less than the distance between the Sun and Mercury at its closest point. In that volume, the total mass is already known from the orbits of the stars, around 4 million solar masses. A small object in size, enormous in weight. The bright part of the ring does not mark the solid edge of anything. It is the light from hot gas orbiting near the event horizon, bent by the extreme curvature of space-time. The central dark region is what we call the shadow. It is not the black hole itself, but the apparent contour beyond which light rays do not return. The shape and size of that shadow are direct predictions of general relativity. They match within measurement errors a black hole described by Einstein's equations. An inevitable comparison arose immediately. When the image of the center of our galaxy is superimposed with that of M87, the resemblance is striking. Two different galaxies, two very different masses, two separate formation histories, yet near the edge both show similar circular structures. Both surround shadows of comparable relative size. That similarity suggests something important. Very close to the horizon, physics becomes universal. The shape of the shadow depends mainly on mass and spin, not on the details of the environment. In 2024, the collaboration presented a version of that same region in polarized light. Polarization reveals the orientation of magnetic fields. In that image, polarization lines draw a spiral structure around the black hole. It is direct evidence of strong magnetic fields guiding the gas as it falls, extracting energy from the flow and organizing the motion of plasma in the innermost region. What were once only light curves and numerical models now have a visible map of invisible forces. Saying 4 million suns sounds abstract. It is a figure that slips by without leaving a mark. To understand it, one must think in terms of weight, not number. A single sun keeps all the planets of its system bound around it. That star dominates Jupiter, Saturn, the asteroid belt, and the distant comet clouds. Multiply that capacity for domination by 4 million and condense it into a space smaller than Mercury's orbit. That is what is at the center of the Milky Way. The size of the event horizon of that object is deceptive. If we could place it where the Sun is, the edge of the black hole would lie within Mercury's orbit. The entire volume of space where gravity is so intense that not even light can escape would fit within the inner region of the solar system. It does not reach Earth. It does not reach Mars. It is a small boundary in size, but absolute in its effect. Beyond that radius, nothing returns. What does extend far beyond is its influence. Mass does not stop at the horizon. It deforms space-time around it, and that deformation is felt thousands of light years away. Not as a special force, but as a curvature that imposes orbits. Every star in the nucleus, every gas cloud, every dense cluster orbiting the center responds to that central mass combined with the rest of the galaxy. The spiral structure, the arms, the disk, all are organized over a gravitational background where the black hole acts as a reference. Our own sun participates in that order. About 26,000 light-years from the center, the solar system traces a slow orbit around the nucleus. A complete revolution takes hundreds of millions of years. During that journey, the sun passes through spiral arms, moves near regions of star formation, and then away from them. The central black hole is too distant to influence our seasons or the shapes of planetary orbits, but it is part of the choreography that defines the galaxy's overall motion. We are a detail in a dance organized around it. There is another dimension that complicates intuition: time. We say Sagittarius A star is 26,000 light-years away. That distance, translated, means that any photon we receive today left the galactic center when there were no cities on Earth, no written language, no complex agriculture. Our instruments capture an ancient state of the nucleus. Every detected flare, every variation, every constructed image is a delayed message. This works in reverse as well. Right now, Earth and the Sun emit light. It is possible that some tiny portion of that radiation travels, crosses the galactic disk, and passes near the center. That light will carry information about this moment, about the composition of our atmosphere, the activity of the Sun, the existence of a planet with complex life. It will reach the environment of the black hole in 26,000 years. By then, everything we know will have changed. Humanity may have transformed, gone extinct, or dispersed. Political and cultural structures will have disappeared, but the signal will continue its path, indifferent to those details. This asymmetry between experience and signal is a direct consequence of the finite speed of light. It forces us to accept a simple yet disturbing idea. We cannot see the center of the galaxy as it is now. We can only speak of how it was when the light left there. The same applies to any distant object. The observable universe is a repository of delayed times. In the case of the central black hole, this temporal difference adds an extra layer to contemplation. While we observe the orbits of nearby stars, analyze their brightness, measure their flares, we do so with data from a very specific moment in galactic history. Perhaps in 26,000 years, the environment of Sagittarius A will be different. It may have devoured a massive gas cloud. Its activity may have increased. It may be even quieter. It is impossible to know. What does seem stable on long timescales is its own existence. An object of that mass, formed over the life of the galaxy through collapse, mergers, and slow accretion, does not disappear overnight. It is a structural feature of the Milky Way, a component as fundamental as the disk, the dark matter halo, or the globular clusters. As long as the galaxy exists, the central black hole will remain its gravitational reference. If you look at a map of the Milky Way with its spiral arms and central bar, there is a point where the coordinates converge. We do not see it in images because dust hides it. We do not feel it because our scale of experience is too small. But everything we understand about galactic dynamics indicates that there, at the geometric center of the bar, rests this compact object. It is the point toward which the orbits of the S-stars, the trajectories of hot gas, and numerical simulations attempting to reproduce the galaxy's history all converge. In the coming years, new generations of instruments will refine this image even further. More sensitive radio telescopes, space-based interferometers, continuous infrared and X-ray observations will allow closer tracking of flares and gas movements near the horizon. Each technical improvement will slightly reduce the uncertainty about its mass, spin, and the exact shape of the shadow it casts on the surrounding flow of light. Nuances will likely emerge, perhaps small deviations inviting a review of some aspects of theory. But the overall picture will not change. At the center of the Milky Way, there is a supermassive black hole,